Good afternoon. My name is Sarah Mathos, and today I am happy to present SATA, the Emergency Air Flight Solution. Before I begin with the presentation, I would like to give credit to the SATA team, starting with Andrea De La Garza, Alexa De La Garza, Deja Hopkins, and Eric Montgomery.
Each member of Team SATA is a senior within the College of Technology's Computer Engineering program. As a team, we have divided our work and will be presenting the topics that we were the most involved with. This does not mean that the team members did not assist with other sections, which we can accurately say everyone was involved in nearly every aspect.
According to the United States Air Force, a study done in 2015 revealed that after 2 hours of a soldier being captured, their probability of being rescued drops to 25%. Additionally, after 12 mission attempts using current UAV devices, only 24% of soldiers were successfully recovered. The SATA team understands that time is essential. Therefore, our mission is to help their mission. The SATA drone will benefit the military by using 5G communication tools.
The transition from 4G to 5G was not simply an upgrade, but 5G literally changed the rules of cellular connectivity. Our focus is on utilizing 5G's flexibility to optimize high-speed data rates. Every other generation prior capped at a standard data rate specific to that generation. However, 5G is flexible and allows for engineers to continue to optimize and increase the data rate. There's no ceiling stopping us. Our way of exploring this concept is through testing out a few modulation techniques to see which one yields the fastest and most reliable data rate.
The proposed topology of our project. The goal here was to create a 5G star network where each UAV will be acting as a node, and they will be able to communicate with one another and also communicate with the ground control station. If one of these drones fails, the drones will be able to reconfigure their network and still be able to talk to one another.
Theoretically speaking, depending on the modulation used, and we can receive a higher spectral efficiency, but at the cost of lower bit error rate or higher signal noise ratio. Our parameters focus on being able to send a specified carrier frequency. How exactly we can measure bit error rate for that at acceptable rate for certain signal noise ratios, and understanding the sampling rates that our computers can handle for those types of modulations used. So the link layer was looked at a very high level and defines how the packets will be encoded and sent at a modulated complex baseband waveform through the transmitter. But the analysis of it and the demodulation, and that we could sample or take bit error measurements at certain pinpoints that we're looking for.
So for our simulation, the objective is to test the USRP communication signal. We do this by transmitting videos and text signals from one device to another, and we do this by testing the parameters and changing them, such as changing the modulation scheme or changing the distances between the USRPs. The first test we did was transmitting a video signal using PSK. Here in the video, you're able to see that one USRP is transmitting and the other one is receiving a video signal.
We were able to do the text portion of our testing between two USRP PC connections using the PSK modulation scheme. So on your left-hand side, you have your transmitter, and on your right-hand side, you have your receiver connection. Right there, those are USRPs. And we're about to see the text come through on the receiver side.
This is a picture of our experimental setup. We set it up as the USRP transmitter, and then we use Sarah's and my computer, and we use those to set it up as the USRP receiver at 18 feet and at 36 feet.
A measure of interest at the receiver side was the bit error rate. To do this, we had to analyze how the packets are formatted to actually get the message bits of each transmitter and receiver. So if you look at the very left side, the block diagram of that VI, it stores the specified message that we're sending, and it modulates it so it's in bits. So it's just a constant message that's going to be sent, and then at that receiver side, we're going to place that code in there to be able to compare them to each other, the transmitted bits and the received bits, but only for the message length. And then from there you take the timing distance, and then you get bit error rate. One thing we need to improve on is being able to receive very low bit error rates. We need to send a very high amount of bits and be able to test our SNR.
Before getting to the point of attaching the USRPs to actual drones, we have to ensure that the USRPs can project their own network. We tested this through physically distancing the USRPs and designating one as a transmitter and 2 receivers being placed at 18 and 36 feet. With the LabVIEW VI that we put together based off a packet receiver and transmitter example, we were able to change the parameters, primarily focusing on the frequency and gain. Our main examples are set at 915 MHz with a gain of 20 decibels. We have the split screen showing the displays of this at 18 feet on the left and 36 feet on the right. We also show the debug screen for each of these distances. These debug screens show the BER and signal-to-noise ratios we measured. Of course, we tested at several instances of gain and different frequencies. This will also display the parameters panel, the display panels, and the debug panels for both 2.5 GHz and 5 GHz.
So while completing this project, we were able to accomplish a few things. Primarily, we were able to first send a signal between 2 USRPs. Secondly, we were able to send a video from the ground control station or transmitter laptop to a USRP. After that, we were able to send a text message from the ground control station to 2 USRPs at the varying distances as mentioned, the 18 feet and 36 feet distances. And lastly, we were able to calculate the bit error rate of the received data for each USRP. The future steps of this project can be broken down into 2 things. First, we would like to replace the PC USRP connection and change that to a USRP and Raspberry Pi connection. It just makes the project a little bit lighter, a little bit more, takes it to the next level and makes it easier to transport. We are going to perform the same operation we performed in this project, sending both text and video signals. And then from there, we would like to use the QAM modulation versus using a QPSK modulation to help us kind of optimize our video streaming.
Here we have our proposed topology, and the proposed topology is based on a mesh topology. For a wider coverage and quicker communication, the mesh topology is considered, and ideally if a UAV at one point in the mission, for whatever reason, is no longer a part of the network, the system should be able to reconfigure itself or maintain other existing connections until the missing UAV is able to rejoin. This topology is assuming that the PIs are completely configured and compatible with the network modulations, and they can perform device-to-device communication features. With the PIs, the first step was to locally access the PIs with a Git bash terminal in our laptops and then make any updates regarding the camera modules. The Pi was then configured and was ready to use, and we placed it across the room and we SSH'd into it from a personal computer and commanded it to capture pictures and videos. Now, right here is the Raspberry Pi camera stream, and of course, for Raspberry Pi, you have to install the operating system, you have to install the camera module, and we eventually tested the camera with pictures and videos. And then we were able to remote access the initial Raspberry Pi with the installed camera module using a secondary Raspberry Pi. Now, unfortunately, we could not attach the USRPs due to the components that were incompatible or no longer having software support. We researched the most common modulation techniques to find one that would not only be the best use for 5G, but for the software and hardware we are currently equipped with. The one that we primarily tested was QPSK, which is a form of phase shift keying, and this is due in part to the wider spectral width, the bit error rate being lower, and it's considered more efficient in everyday environments. However, QAM is considered to be better suited to 5G because it enables more data rates to be transmitted per 1 Hz, which means a higher spectral efficiency, which means it is enabling more information to be carried over a limited amount of spectrum. QAM is not perfect though. Higher order QAM modulations like 256 QAM have higher SNR ratios, which means higher noise levels mess with this specific QAM. I would like to also note that small cells for 5G have suitable conditions right now for higher orders of QAM. Between using the QAM and Raspberry Pi connection, we would be able to advance to the next stage of prototyping, which would eventually allow us to implement this into actual drones.
To conclude the project, the golden circle can be referenced back to The Golden Circle asks us the three key questions that was established in the beginning of last semester. First, why are we doing this? The SETA team is dedicated, and we honestly believe that there could be a more powerful way to benefit the military through a communication system. We recognize the importance of developing a more convenient way to improve the military's missions with the use of a network-compatible UAV system. How are we doing this? The plan is to make a device that is simple and yet resourceful to use. This device will allow us to communicate and receive data at a far range utilizing 5G techniques and modulation. And what are we doing? SETA offers the most compelling and simple way to manage military search and rescue missions. We're providing an efficient device that uses 5G technology for wider coverages and quicker communication to execute search and rescue missions more successfully.